And so for the majority of the talk, I'll be talking about high dimensions in terms of high dimensional summary statistics. But just for completeness for this audience, I'm going to mention at the end some extensions that have recently been done by other authors for high dimensional parameters. So that's the main work is with Suen, Chris Giovanni, Anthony Lee, and David Knott. And that last bit I'll be talking about was with Victor Mcmc and Scott Sisson. So I'm going to start out giving a bit of background on likelihood-free methods and approximate Bayesian computation. Then I'll give a motivating example, and then I'll go into the main method for the talk and extensions to higher dimensions. Okay, so assume we've collected some data y, and it's believed to follow a stochastic process with parameter theta. Then in Bayesian statistics, we're interested in sampling from the posterior. So P of theta given y, which is proportional to the likelihood P of y given theta times the prior P of theta, which is our beliefs about the parameter independently of the data. And a really popular method to sample from the posterior is Markov chain Monte Carlo. This has been mentioned previously, but since I'll be using it, I'll just go into just a little bit more detail. So the idea is to construct a Markov chain that has the posterior as the invariant distribution. And a common MCMC algorithm is Metropolis Tasting's MCMC, where you make some proposal theta star, and you accept it with this probability here, where Q is the proposal density, which could be, for example, a multivariate normal random walk. So this is really popular, but for complex models, you might not always have an analytic form for your likelihood, or the likelihood function might take too long to compute. So you don't really want to use this in its form that it's shown here. So in that case, you might consider likelihood-free methods. So you use likelihood-free methods when the likelihood function is intractable, but simulation of data from the model is feasible. And it is possible to work on the full data level, but generally it's common practice to reduce the data to a sort of set of summary statistics, and we denote that SY. Then the objective is to sample from the summary statistic posterior, which is proportional to summary statistic likelihood times prior. And since our likelihood function is intractable, often so is our summary statistic likelihood. So we use likelihood-free methods that avoid the computation of both of those things. And the current state-of-the-art method for likelihood-free inference is approximate Bayesian computation, or ABC. And the idea behind that, as Fabrizio mentioned, is to compare the simulated and observed summary statistics using non-parametric methods. The basic method, and this could be implemented several ways, but I'll be doing it inside MCMC. So in MCMC, you make a proposal theta star. Then based on that value of theta, you simulate n IID data sets from the model based on theta. You calculate the n summary statistics, and then you replace your intractable summary statistic likelihood in your MCMC with this thing here, where rho is called the discrepancy function, which could be, for example, the Mahalanobis distance. K is the kernel weighting function that's designed to give high weight to low discrepancies, and that involves a bandwidth epsilon, where epsilon is called the ABC tolerance, and we want epsilon to go as close to 0 as possible. So if you had epsilon of 0, then that's saying the distance between your simulated and observed summary statistics is essentially 0. But reducing the value of epsilon is computationally expensive. So we've got to have a balance there. And in an MCMC serial computing environment, n equals 1 is close to optimal. So basically, you just simulate a data set, calculate a summary statistic, and then replace your intractable summary statistic likelihood with just this thing here. Now, this has been useful in a lot of applications, but it has got several disadvantages. It's highly sensitive to the choice of the tuning parameter epsilon, to the discrepancy function, and to a lesser extent, the kernel weighting function. And there's no standard way to select epsilon or to select the discrepancy function. So people who've used ABC before would be familiar with that difficult task of trying to choose a good value of epsilon. And ABC suffers from the curse of dimensionality with respect to the size of the summary statistic. So as the summary statistic dimension increases, it becomes more and more difficult to tune epsilon and to choose discrepancy functions. So this is kind of where the high dimensional part comes in. We're trying to extend or improve this quality of likelihood-free methods. So I'm going to use one example throughout, partly because it's an interesting example, partly because all of the papers used it. So I'm sorry, it's only two-dimensional parameter, but it's got 145 dimensions on the summary statistic. So cell motility and proliferation are important parts of many biological processes. For example, they contribute to skin cancer growth and wound healing. So if we can find good ways to estimate the probability of cell motility or movement and the probability of cell proliferation or reproduction, then we might be able to better assess different methods to, say, improve wound healing. One way to investigate these processes is through a Scotch assay. So cells are left on a dish until they completely cover the dish in a single layer, and then at that point you make a scratch through the centre, and you take photos at regular time intervals, in this case every 5 minutes for 12 hours, until that scratch closes up again. Then you want to turn this into data, so you approximately map the cells onto a rectangular lattice, and you end up with a binary matrix of cell presences and absences, where a 1 obviously indicates a cell presence at a particular location. We use a random walk stochastic model for this statistical model here. So in each time step, cells are given the chance to move to a neighbouring location with probability PM, and they're given the chance to birth or to reproduce to a neighbouring location with probability PP. So it looks like actually this isn't working. This is meant to be, at the beginning, at the bottom part where it's blue is where the scratch has been made. So ideally, if this was running, it would be showing that those cells at the top will be moving down and closing up that scratch, and that's kind of what our images look like. And this is simulated data. I'll be using this simulated data for all the examples. So the probability of movement is 0.35, and proliferation is 0.001. Okay, so our aim in Bayesian statistics here would be to obtain the posterior distribution for PM and for PP, and then we can convert these into biologically relevant diffusivity and proliferation rate. Now, the model has no tractable likelihood function. We can't write down a likelihood function for that stochastic model I showed you before, but we can simulate data from the model, so it's an ideal candidate for likelihood-free methods. The summary statistics that we use, because as I said, we often reduce data to summary statistics, are the Hamming distances between adjacent lattices or images and the total number of cells at the end of the experiment. And this is 145 summary statistics, which is too large for conventional ABC. So this sort of problem is the sort of problem that might motivate alternatives. And specifically, we're going to look at parametric alternatives. So the idea is it might be possible to overcome some of the drawbacks of ABC by using a parametric approximation to the summary statistic likelihood instead of the non-parametric one that you use in ABC. And the one that we use is based on a multivariate normal approximation. So Simon Wood described in his 2010 paper this idea of replacing an intractable summary statistic likelihood with a normal approximation. So normal approximations are everywhere, suitable when the summary statistics are subject to the central limit theorem. Often you can transform to multivariate normality, or if you've got summary statistics from indirect inference, then those will often be approximately normally distributed. So this is often, it's often convenient, it's often going to be quite useful and relevant, but it's also really convenient to work with. So we refer to a Bayesian version of the synthetic likelihood from Simon Wood's paper as Bayesian synthetic likelihood. The basic idea, now this looks kind of similar to MCMC ABC. So for a single iteration of MCMC, you would simulate n IID data sets from the model based on theta, calculate the n sets of summary statistics, and then from that you calculate the sample mean and sample covariance of the summary statistics. Then you replace your intractable summary statistic likelihood with this, this thing here. And the only tuning parameter then is n. So in ABC you have the tuning parameter epsilon. Here we have the tuning parameter n, which is the number of simulated data sets from the model for a single value of theta. So the target depends on the multivariate normality assumption for obvious reasons, but it also depends on n, the number of simulated data sets, because the multivariate normal PDF that you get using the estimated mean and covariance from n simulated data sets isn't an unbiased estimate for what you get if you had the true mean and covariance for that value of theta. So here's some results for BSL, the marginal distributions. So in black is n equals 2,500, in pink is n equals 5,000, and in blue is n equals 10,000. So you can see here that the distributions are remarkably insensitive to the value of n that you've selected. And in this case, n equals 5,000 was most efficient, but there was a range of 2,500 to 10,000 that was quite efficient. So this is a big range of n, which is kind of suggesting it's maybe a little bit easier to tune n here than it is in ABC. Also, you can see at the bottom in the black line is the true value, so we're covering that quite well. Now, comparing that to ABC, we've got in here, black is ABC with 3 images. So I mentioned this is really challenging for standard ABC with 145 summary statistics. So previously, people have done similar work, and they've looked at a subset of only 3 of the images. So you might imagine that you'd lose a bit of information, for example, about the cell movement, and that's what happens. So black is ABC with 3 images, pink is ABC with all images, grey has a regression adjustment on ABC to give it that extra advantage, and blue is BSL with all images. So you can see firstly, in terms of the probability of cell motility, we're getting more information about that using more than 3 images than if we used, using more than 3 images than if we just used 3 images only. Which isn't surprising. Also, you can see that we're getting quite an improvement from the regression adjustment. Now, we chose epsilon in ABC to give similar efficiency to BSL, so that the fact that that regression adjustment is helping is kind of indicating that BSL might be more efficient. And for probability of cell proliferation, or PP, it's interesting to see that you actually get more information about that using only 3 images than you do using all of the images. And that's because it's really difficult to tune epsilon in ABC. And so our results are kind of being affected by that here. And the results with BSL compared to ABC with the regression adjustment are quite similar. So we use 16-core CPU, and the average model simulations per second is 75 for ABC and 820 for BSL. So we get quite an advantage in terms of parallelization. But there are, of course, some drawbacks to this parametric approximation. One is that the distribution of the summary statistics should be roughly normally distributed. And there's been some work by Chris and Zoen and others that have looked at trying to relieve that, but I'm not going to talk about that today. But I am going to talk about the number of simulations per iteration, n, which needs to be large depending on the size of the summary statistic. So I'm going to talk about some work that we've done on trying to reduce that issue. And then the last part is the reliance on Mcmc to explore the parameter space, which isn't ideal in high dimensions. It can be very inefficient. So if you've got a high dimensional parameter, you might want to use an alternative. And the last part of my talk is going to cover that, but I'm including that for completeness. I wasn't directly involved in that work. Okay, so in terms of the first part, extending BSL to high dimensional summary statistics, so we need to choose a large value of n in the standard method, because we're estimating the mean and covariance of the summary statistics based on those n simulations. So to do that for a 145-dimensional summary statistic, we needed large values like n equals 5,000. But that is many model simulations, and often that's the most expensive part of likelihood-free methods. So we're looking at enforcing some sparsity into the precision matrix using the graphical lasso method. So I'll describe a bit more about that in the next slide. But the interpretation is that you're implying there's some conditional independence between summary statistics. And in the case of the summary statistics being taken over time, in our particular example, that kind of makes sense. So it's a reasonable assumption as well in this example. And we refer to BSL, accelerated with graphical lasso, as BS lasso. So what we're doing is estimating the sparse precision matrix so that it's sparse, and we're maximising the penalised log likelihood, so it's the original log likelihood, and then we're subtracting off this term here, where if you make lambda larger, you'll induce more sparsity. And the value of lambda, as I said, controls sparsity, and that value is also tied in with n. So if you have more model simulations, you don't need to induce as much sparsity, whereas if you've got n really small, you'll need to get a more sparse estimate of the precision matrix. The standard approaches in the literature for graphical lasso for choosing lambda would be BIC and the cross-validation error. But we're choosing the value of lambda so that we can get good MCMC mixing. So that motivates this new method for choosing lambda. In the literature, it says if you've got an unbiased estimate of the likelihood, you should have a standard, and you're doing that in MCMC algorithms, you should have a standard deviation of the log likelihood of roughly 1. And in our case, we found that roughly 1 to 2 works well. So what we're doing is we're aiming to get a standard deviation of our log synthetic likelihood of roughly 1.5. So the idea is that we have multiple different values of lambda. We generate a bunch of summary statistics, get the sample mean, and the covariance estimate with those different values of lambda, and then we choose the value of lambda that leads to standard deviation of the log synthetic likelihood of roughly 1.5. Okay, so here's just some results for the different values of lambda that are chosen for different values of n. So on the top, we've got our method. Then in the middle, we've got BIC, and at the bottom, we've got cross-validation error. So you can see that our method is choosing generally a smaller value of lambda than the other methods. So we know that's going to give good mixing because that's the way that we've chosen it. And we also know it's going to be closer than the other methods, BIC and cross-validation error, to the standard BSL because the value of lambda is smaller. So that's indicating that this method, it makes sense. In terms of the results that we get for this example, at the top here in this table, we've got the results for standard BSL with n equals 5,000. So for each value of theta, you're simulating 5,000 data sets and calculating summary statistics. You can see the acceptance rate's 21%, and the normalized effective sample size is roughly 8 for the 2 parameters. But if we use the BS lasso, we're going to get a similar acceptance rate and a higher normalized effective sample size. So essentially, we're getting some nice improvements in terms of efficiency. And if you look at the posterior distributions, in black we've got BSL, and then in red, blue, and green we've got varying values of lambda and n, where the value of lambda is highest for red, so that's got the most sparsity. And all of these approximations here are appearing quite similar. So we're getting similar approximations, but more efficiently. Now, there is an alternative, which I'm going to quickly mention because this will be relevant later in the talk. And the alternative shrinkage is based on a method from Wharton's paper in 2008. The goal is to maximize this penalized likelihood. So it's similar to before, except the term we're adding on now is this value gamma times the trace of the inverse correlation matrix. So it's just kind of a different way to do our sparsity. And the benefit here is that we have a closed form solution for our covariance matrix, whereas previously we had a convex optimization problem, but there wasn't really a closed form. Now, this last part of the talk, I'm running a bit quick, so maybe I can go into more detail than I thought. This last part of the talk is on extending BSL to high dimensional parameters. And I thought this might be interesting to this audience, but as I said before, this is work by these people here. So I've learnt about it a bit through my supervisor, but it's not directly my work. But the idea is that MCMC can require a large number of iterations to explore the space if you've got a high dimensional parameter. So instead, you might want to do an alternative to MCMC. And the alternative that is used is variational Bayes. And so basically, it assumes a parametric form for the posterior, which we denote Q. And it's quite handy that Tamara gave a tutorial on that on Monday, so hopefully people know a bit about it. But the idea is that you can significantly reduce the computational cost in approximating the posterior if you do this rather than something exact like MCMC. So variational Bayes sets out to minimize the Kullback-Leibler divergence, or KLD, between our approximation Q and the posterior. So the benefit in Bayesian statistics of that is that this is the Kullback-Leibler divergence, and then you can write it out in this form. So our annoying normalizing constant of the posterior comes out, and instead we're minimizing the Kullback-Leibler divergence, which amounts to minimizing this minus L, or maximizing L itself. and L is called the variational lower bound. So basically choosing our parameters of our parametric approximation is essentially just maximizing this L term here. Now in VBSL, we're looking at summary statistics of the data. So we're minimizing the Colb-Labler divergence between this Q and between the summary statistic posterior. So Robert Cohn and others have done some work on this kind of idea for ABC, and this is the extension that's been done for Bayesian synthetic likelihood, which is the parametric alternative. So in this case, we're looking at a multivariate normal Q, so multivariate normal variational approximation. And so this is just a separate multivariate normality assumption to synthetic likelihood. So we've got two going on here. We're assuming multivariate normality of the summary statistics, and we're assuming multivariate normality of the posterior in a way. And the parameters of that are the mean and the covariance. So we've got to estimate those. And the way to do that is to use stochastic gradient variational descent for the optimization. I'm not going to go into too much detail about this, but basically you want the derivative of L term. And so the idea for stochastic gradient descent is to start at this initial value for the mean and covariance, and then to use this rule iteratively until you get convergence. And it's good if you can get an unbiased estimate of this derivative term, and in the paper they use an unbiased estimator for the log synthetic likelihood. So theoretically that doesn't depend on the value of n. There are lots of tricks that you can use to improve the efficiency for that. For example, including control variates, computing some parts analytically, reparameterization, and adaptive step size choices. But I'm not going to go into details of all of that. So here are some results. So on the left, we've got the lower bound, that L term that I mentioned earlier, and you can see that we're converging to the value roughly about 40 iterations or a bit less. Also, I can say here, sorry, I forgot to say earlier. So black is essentially BSL. Red is VBSL, so BSL with variational Bayes. Green is BSL with variational Bayes and graphical lasso, so Schrinker's estimate on the covariance of the summary statistic. But you can tell kind of here that we're getting roughly the same approximation for the two different parameters. Depending on the method, it's kind of similar, and with VB, it's a lot more efficient. So a lot less simulations from the model to get that approximation. Now, the downside of that example I used was that it was only two-dimensional, but variational Bayes is often used for high-dimensional parameters. So if you had a parameter of dimension 100, then the number of variational parameters that you'd be wanting to optimize over for your VB would be 5,150. So that's not really ideal. So what they do in their paper is to parameterize the posterior covariance using factor analysis. Okay, so those were the extensions to high-dimensional summary statistics and to high-dimensional parameters. Now I'll just give a quick summary of BSL itself, mainly, and then a little bit of the extensions. So the good things about BSL are that it requires less tuning than ABC. It can be more computationally efficient than ABC, and it can use parallel computing really well. And it also can be accelerated for high-dimensional summary statistic, as we saw with the BS lasso work. It may not be as robust to model misspecification, but there's ongoing work that's been done on that. And unfortunately, it can completely fail if you've got really highly irregular summary statistics. So if you're interested in our BSL paper, we have an example where we've got non-normal summary statistics. There's some skewness there, but they're still kind of regular. They're not extremely strange. So what you find is that BSL still performs well, but if you had highly irregular summary statistics, it can fall over, but ABC will still work. And in terms of ongoing and future work, there's some work on asymptotic properties of BSL, recycling simulations, BSL under model misspecification, and then in terms of reducing that multivariate normal approximation for the summary statistics, as I mentioned earlier, Chris and Zelen and others have looked at more flexible approximations there based on copular models. And then in terms of reducing that parametric approximation of normality in the VB, you could look at more flexible variational distributions like mixtures of normals or copulars. Thank you.